Okay, we are on to example 16. Yesterday we proved a result, and if you could recall, to prove that simple result, okay, what was the result? We proved that limit as x tends towards a of modulus x, we proved yesterday was like that, remember? Okay, so continuing on the same similar thing, we are going to look mod A, right? Thank you. Yeah, so continuing on the same similar thing, we are going to look into how we can evaluate the questions like in example 16. Let me ask, have you done it already? The boy behind you? Good. Okay, let's hear from some of you. How did we go about this? There's a small minus there. Can you see that? X tends with 0 minus. Brilliant. So when you open up the modulus, you need to put a x squared minus 3x. Right. Then this becomes limit x tends towards 0 minus. This can be x minus 4 and x minus 3. I can hear talking behind. Okay. Seriously, no? You can talk. Just talk softly with the person next to you. I made mistake, is it? Okay. Can you just talk softly with your friend next to you? You cannot try to talk across tape because it won't work, because it's going to cause a lot of disruptions to us. Okay, so class, we do not want you to jump from this slide to this slide immediately, especially those who just write down the answer. We don't want that, We want you to show working such as this, so that we know that you know. You know what I mean? Right, this is example 16. Okay, for those who have not tried 17, you can try 17 now. Now for question 17, I would suggest that this question, right, this part here, I actually prefer that you write what write as x tends towards that. Otherwise, it can cause a little bit of confusion, right? So I prefer that you write like this for the thinking below, the limit. So this becomes limit x tends towards minus 1 plus. Okay. Now, if x tends toward minus 1 plus, the numerator doesn't change. How about the denominator? Think of numbers which are minus 1 plus. What are they like? Negative 0.99, Negative 0.999 counting. So if you think of such a number, then you know that the denominator is going to be a positive, So this is going to be just x plus 1. Then limit this gives you x plus 1, x plus 1, and then this gives you limit x tends towards minus 1 plus x, and therefore this could be minus 1. Okay, this is example 17. In the other class, they told me that 18 is actually harder. No one? Okay, that's good to know. In question 18, right, we are given the case where x tends towards 3 plus. A show of hands up, who have done 18? Okay, right, so for the vast majority, maybe it's a good one to try now, 18. Okay, for question 18, right? For question 18, you want to note that when you are tending toward 3 plus, so you think of numbers that are considered 3 plus. What numbers are like 3 plus?
3.00001.
Brilliant. So therefore, this portion here will be positive, right? This portion will be positive. So therefore, you will open up this thing as just x squared minus 8. How about the 2x minus 7? If x is tending towards 3 plus, what do you think about 2x minus 7? So therefore, when you open up the modulus, right. And then on the denominator, is again positive, right? And now let's do the arithmetic. On the numerator, what do we have? Right. Minus 15. Hey, hi, come in. The SSCF form, is it? Yeah. Okay. Then when you reach this stage here, you want to actually now make use of the factorization. And then this gives you limit and finally we have 3 plus 5 is equals to 8. Good. The water. Do you have water? You all live in boarding right now. It's nice, right? Living boarding is very nice, right?
Oh yeah, you guys.
But because living boarding is good because you get all your friends, Then in the night, in the evening when you're freer, you can meet up your friends to chit chat or to do homework together. That's very nice. I wish I had gone through the same thing like you. Yeah. Okay, example 18. Are there issues that you wish to raise? Okay, the next one, we want to delve into the infinite limits. There are a few statements here pertaining to the value of the limits being infinity. Class, when you write this, you are very careful, We don't mean that the infinity is alright, we don't mean that, We are just saying that the value of the limit is humongous, very, very large. That's all we mean, Now, you want to be able to translate this statement into a graphical diagram. If you say that when x tends towards, in this case, the a plus, fx goes to infinity, graphically, how do you think it looks like? say if this is your x-axis and this is your A, what it basically means is when you are very near to A from the right, the graph actually goes up infinitely. Which means at the point A, you actually have a vertical asymptote. Right. Okay. So for all these statements, you want to be able to translate them into a diagram like what I've drawn for you for the first one. And right below, there is actually a statement pertaining to this now. In definition 17. Definition 1.7, sorry, 1.7. Yeah. It talks about the vertical asymptote. And then we arrive at the QC, quick check. Let's hear from the, next to, okay, I better get no names. Sorry, may I know your name? Huh? Okay, I can't hear you. What's his name again? Gregory. Hi Gregory. So what do you think about quick check? Okay, what do you think? Do you buy in? I can't hear. You want to say? Your friend will say for you? Okay, this statement, class, if you do not know it, I want to tell that this statement is actually false, Now, why is this statement false? Because it is potentially possible for you to have, right? Yeah, potentially your diagram might look like this. You indeed do have an asymptote, and FA is still well defined. You know what I mean? And then we have these. Like the first one again, 19a, right? When x goes towards 0, 0 plus. Of course, someone says, can't I just say D and E? Technically, you're right, Technically, you're right. But it is more informative if you say like this. Right, it's more informative. Okay, so when x approaches 0 plus, which means x goes towards 0 from the right hand side. So imagine numbers such as 0.001, 1 divided by 0.001 is indeed large and positive. So likewise, you will say that this one is. And how about the third one? Right. Again, if you say D and E, you're actually quite right too, right? Because the left and right limit actually are infinity. Let's try the second one. Infinity, that's right. This is infinity, and in this case it's also infinity, Okay, for the next one, I like the class to say together again at the count of 3 again. Next one again, this one. Okay, in unison again, at the count of 3. Are you ready? 1, 2, go. Very good. Yeah, some people think it's positive infinity, you know. It's negative infinity because cosine near 2, right? Cosine 2, right, is actually negative, you know. Why is that so, no? Right, pi over 2 is about 1.57. So 2 is beyond pi over 2, and therefore it falls into the second quadrant. Right? In the second quadrant, cosine is negative.
Oh, that's how it works, right?
Right, Ethan, that's right.
Yes.
Okay. I feel sorry for Gary. I know he's tired. Yeah. Gary. You're sick, is it? Okay. You want to go back to your room to rest? It's recorded, no? Gary, it's recorded. So in case you missed it, no? There's always this broadcast on YouTube. In case. No, I'll post it on YouTube. I find it easier on YouTube because the Microsoft platform sometimes works, sometimes doesn't work, sometimes the access problem thing. Yeah. Okay, and this will be positive infinity. Because when x goes towards 2 minus, the denominator is going to be negative, right? And the numerator is negative, that's why it's positive infinity. So for the reason, this is, do you say neither or neither? Either or either? Okay. Root or root?
One is British, one is
Yeah, one British, one right. For the next one, right? Okay, for the next one, when x tends towards -3 plus, you can think of a number that is -3 plus, you know, like -2.99. So the top is negative, yeah, right? And the denominator is positive. And the denominator is a positive and a very, very small number. So it results in a negative infinity. And for the next one, when x approaches negative 3 plus, this is always positive, and this is also positive and very small. So in the end, you get a let's say together the answer for the last one, okay? At the count of 3, the class will echo, okay? Are you ready? On the count of 3, 1, 2, 3. It's a scam. It's a scam. Okay, for the next one, the limit when x goes towards 0. No, that's explanation. Okay, now going back, since you there's an explanation. You want to do a factorization. This one is going to be 2 into x plus 3. And then 3 plus x. You cancel all these two. Okay? Okay. When x is very near 0, when x is very near 0, no? Okay, I was just kidding. Thank you for pointing out. Okay, so we can do a cancellation. Now we ask, when x is very near 0, the numerator is negative. The denominator is a very small positive number. Right? Small and positive. So altogether, we are going to get negative infinity. Right, this is example 20. Is she out now? Oh, she just sleeping. No. Let her be. It's okay. Let her be.
Okay, sleep.
Not that I didn't notice, just that I always ask myself this question when my students sleep in class. If I wake the person up now, the next lesson the person will still be sleepy. Then he will suffer the next lesson and so on and so forth. So I thought maybe if she sleeps here, maybe next lesson she should be energetic. Okay, the next question. Does G have a vertical asymptote at x equals to 3? To answer this question, you basically ask yourself, what is the limit when x goes towards 3? Okay, maybe let's start with 3 minus, when x tends towards 3 minus. So ask this question of when x approaches 3 from the left. Let's see what happens again. For the numerator, right? When x tends towards 3 minus, what can you say about the numerator? The numerator will be something negative. In the denominator, this one is going to be something negative and small, right? Okay, maybe I did too prematurely. No? I should actually do some cancellation first. I rewind, okay? Then rewind. Good thing about technology, I can rewind quite easily. I want to do a factorization first, to clean it up a bit. To clean it up first. Okay, maybe we do this one first. Then you ask when x tends towards 3 minus, the numerator will be positive. The denominator will be a negative but very small. So all in, it tells you that this will eventually be a negative infinity. Okay. This alone is enough to conclude that x equals to 3 is a vertical technically, you ought to also look at how it behaves when x goes towards 3 plus.
It's
Yeah, right. If you do this, right, it is do this. It is indeed infinity. And therefore it tells you that on the other end, on the other side of it, is also a vertical asymptote. Geometrically, could you now make an attempt to draw geometrically how it actually looks like? If you draw this geometrically, this is 3. Geometrically, how does it look like? It says towards 3 from the left, we have negative infinity. It means go down this way. Towards 3 from the right, we have positive infinity. So geometrically, the graph will be like this, near 3 on the left and on the right of 3. Okay, then the next thing is we want to check, does G have a vertical asymptote at x equals to 4? Okay, now can you all try? What happens when x goes towards? So the same thing goes now. You want to check now, limit as x goes towards 4 minus of your gx. Your gx is x squared minus 16 over x minus 3 x minus 4. And this gives me limit x goes towards 4 minus, on the numerator I'm left with x plus 4 over x minus 3. So that when x approaches 4, this is it. To check for asymptote, right? To check for asymptotes. For checking asymptotes, we might want to do this. To check asymptotes, yeah. To check for asymptotes. You're right. To work out the limit, you don't have to, You're right. So the point given by some of you in front say, I shouldn't have done it as 2 different limits. It's true. Just that because if you're checking for assistant or asymptote, you might want to do just left and right, Yeah, she is right. So she says this will lead to the same conclusion. Geometrically, how will the graph be like? So geometrically, at the point 4, we know that at the point 4, we know for sure that at the point 4 the graph is not undefined, right? Then when it's more than 4, it is something going up. Is lesser than 4, I believe it is something that, okay, let's see, this positive, this negative, this negative, positive. I think it's still positive. I think it's still positive. Something like that. Something. I think both sides positive. Let me check again. When it's less than 4, this is negative. Negative is positive. Less than 4. Yes, positive. It's a positive number. I think maybe. Okay, I'm just second guessing. I don't know the exact graph. So I think maybe look like this. Maybe. Okay, it could be the other way around. Okay, keep it. Whatever it is, I want you to note that that at the point in question, while it is undefined at the point in question, the graph actually have a limit at x equals to 4, as we have calculated.
Yes.
I think my direction of graph is wrong. I think the graph should be like that. Yeah, the other way around. Thank you. Yeah, the other way around. Because from here, after you factorize and cancellation from this function, I just do some mental drawing in my mind, you know. So I think the graph should look like this. Yeah. Or you just put in some values inside to check. Yeah. Huh?
Or you can use Desmos.
Desmos, that's right. Right. Your calculators are still working? Okay, we don't need yet, don't need, but soon, yes, soon. Okay, question 22. Okay, can you try right now? Which of the following statement is, okay, don't say it, we'll say together as a class. Okay, first and foremost, f is not a function. By the way, do you know how to check if something is a function? What do you do?
Vertical line.
Brilliant, you learn well. Vertical line test. Okay. Whenever I pose a question to my daughter at home, right, she doesn't want me to tell her too much first, you know. She won't want to try like all of you like. So therefore, you should try. If you are ready, on the count of 3, we'll say out the answer together very quickly. Are you ready? 1, 2, 3. I didn't hear anything, no? Okay, why this is false? Right, because x is a function, because all the vertical line cuts the curve at most once. Yeah. Why is this statement false? The left and the right limits, this one right, left and right limit don't agree. Why is this thing false? Same reason, right? And then it says left limit it's not defined, it's not true. The left limit is actually 2. Right now. Okay. Okay, another quick check. Suppose the function is defined on real numbers, and this limit is, which of the following must be true? Okay, you want to ponder first, and then we say it together at the count of 3, okay? My lesson with you today is up to 9:30, no? Do you know? After 9:30 is what? Recess for 1 hour?
30 minutes.
Okay. Okay, if you are ready, on the count of 3. 1, 2, 3. D. Right, D. Why is it D, you know? Because we know that the limit and the function value may or may not. So these two are not guaranteed. Okay? This is interesting, you know. Do you remember when I said about x going towards A? In this notation, right? In this notation, when you say x goes towards A, right? X is never A, you know. Let me look. X is never A in this statement. But that doesn't mean that
By cross the line at like some other point. That's it.
right. Because you can potentially have a graph that look like this. while this statement means that x is never a, the function could have been like that, you know, and the function could potentially be the value of L throughout. Is possible, right? It is possible.
Possible.
Yeah. Because it say okay, must be true. I'm showing you that that it is possible for you to have fx equals to L. So therefore, need not be not equal. I'm trying to disprove, right? Need not be not equal. It can be L throughout even, you know, or it can even be just L. Like for example, if you have maybe this A and the graph is like that, and then this is L. So in that sense, fx can be L also, no, right? Which means you got very careful on this thing, no. While we say x is never a in this notation, that doesn't exclude the possibility that the function itself can be L, you know. Okay, I guess the boys in France are having good fun. It's free entertainment, Okay. Now we are moving on to a new thing. Up to this point, we have been delving into this thing called limits.
Yes, which is the foundation of calculus.
Thank you for that. Yeah, it's true. Connected to this topic is continuity. It may be high sounding, but geometrically it is what you see to be. Right? Continuous function means there's no brokenness. That's about it. So this concept is a very easy concept. Just that in math, right? In math, you are given a function, and then you are told show that the function is continuous at a point. Say at a point. For example, if you have a continuous function, right? If you have a continuous function, say like this, and then the question say, show that the function is continuous at x equals to a. For the start, people who see this for the start, they'll be wondering, no, what do you want me to show? No? Because you say to answer the question, you probably say from the graph it is obvious. However, in math, right, geometrical consideration is not taken as foolproof on you. You have to actually use analytical method. That means by way of calculation. It's a surer way. Okay. So therefore, class, you want to note that when you're asked to prove that a function is continuous at a certain point, you cannot say refer to the graph. Therefore, it's obvious. You'll get 0. You are required to prove these 3 statements. You know that these 3 statements hold. Then someone clever among you say, Mr. Lim, actually, he says 3 covers 1 and 2. Technically, it's true, no? You think about it. If the third statement is true, right? Then this number must be defined. You know what I mean?
Oh yeah.
And then this limit must exist.
Yeah.
So technically,
Only the third one is correct.
no.
Only the third one is correct.
Technically, yeah. If you have the third one, you have the first 2. However, for beginners, in this module, in the AP exams, you are required to show and then say this. In a minute. You have to do part 1, part 2, and then marry them on part 3. And only after you marry them in part 3, then you say, aha, it is continuous. In a minute. Like it or not, you have to do it that way, you know. Right, okay? So, like in this example 23, okay, in this example 23, because the function is not so-called defined for you. So in this part of example 23, it's just precursor is to let you get used to these conditions, and therefore in example 23, based on the graph, you want to ask at the point A, is condition 1 satisfied? Yes. So you put a tick. Right. Put a tick. At the point A, is condition 2 fulfilled? The limit at the point A based on the graph? Yes. And is condition 3 fulfilled? And lastly, you have 4 yeses like AGT, you know. Do you watch AGT?
Yes.
It's very entertaining. Yeah, it's very, very entertaining, though. I watch it a lot with my daughter, and I find it very entertaining, you know.
Yes.
Those who have not watched the AGT, Americans Got Talent, you want to try to watch it. It's very nice. You see the perseverance, the kind of determination the competitors have. And actually, my daughter somehow enjoys it more when the participants are criticized, condemned by the judges. Very funny, you know. And then the reaction from the contestants, you know, it can be quite extreme. Some will start to curse and swear. I remember one episode where this contestant threw the mic onto the floor, you know, and said some curse words, you know. Americans Got Talent.
Unless it's out of the graph, it's okay, that's all.
Okay, class, you have a job to do. B, C, D, E. Now. In the meantime, let's revise names. Yu Tong.
Yeah.
Okay, I remember your name. Kailash. I know Jethro. I know Gary now. The one in Gregory. Greg. Okay, call him Greg. Okay. Sorry, I may mispronounce name. Sorry about it. The blue guy. Jireh, okay. Jehovah Jireh, the same Jireh, J-I-R-E-H. Okay, Jireh. Okay, so I started with 5 names first. I slowly get to know the rest. Okay, 5 names first. Oh, you better get to know your name because you sit right in front and then you're tired today. What's your name? Ting Hui. Ting Hui, yeah, I remember Ting Hui. Okay, Ting Hui, are you alright today? You're feeling unwell? Okay, if you feel unwell, you can just go back to barrack, you know. Are you all done? I can see the boy. What's your name? Christopher, you're done, right? I can see that. Christopher is done. Okay, let's wait for a little while more, then we compare. So for those who have done, for those who haven't done, don't look up, you know. For those who have done, you want to compare. For those that have done, you know, you want to compare. No, for those who haven't tried, you shouldn't.
Because negative infinity is considered as like not existing.
Yeah. Infinity is not a number, yeah, for the reason. Yeah.
No, the system we are regarding infinity as a number.
Right. Okay. Yu Tong, Ting Hui, your name?
Ryan.
Ryan, Christopher. Okay. Alish, Jethro, Ren, Gyro. Okay. Wen Yu, you finished it? It's all correct? I remember her because she's in the SMP, you know. Yeah.
SMP.
SMP.
Minecraft.
Part D, is it? Part D, why doesn't it have a... Okay, infinity, right? The part D, right? Actually, it is infinity right now. Whether it's negative infinity or positive infinity, these are D and E, no? Then again, we have a number system where there's something that is not in the system, infinity, actually, infinity is not the part of real number system. So, did I share with you that actually maybe I think our number system is flawed, Maybe some of you can come up with a better number system that, will eradicate the x squared plus 1 equals 0 equation. And then if you do have a better number system, tell me first, Don't tell anybody else, tell me first.
One is still idea.
Huh?
One is still idea.
I won't, trust me, I won't. In the research world, there are all of stories about this, that the professor steals the idea of so-called the student and then wrote the paper as his own. But to the professor, he thinks it's justifiable because he has given you lead in some areas, and then maybe because of this, he let you to think through, and then you came out with this idea. So to engulf it as his own paper and with you as a second name, to that is justifiable, no? Yeah, second name, yeah. But I won't, don't worry, I won't. So you tell me the great number system, I won't, I will just honor it, I'll say it's yours. You didn't fill in the rest. You think, right? Ting Hui. Oh, sorry, I mixed up the name. Ryan, what's the name? Ting Hui. Yu Tong. Okay, I mixed up. Ting Hui, Yu Tong. Okay. Ting Hui, Yu Tong. Wow. Okay, Ting Hui, you didn't fill in the rest, no? I noticed. The no and yes.
I fill in the no, yes.
You fill in the yes, so the rest are default no.
Yeah.
Clever. Okay, example 24. You want to try this question, To check that a function is continuous or not, as I told you, you have to do it the way we talked about the 3 steps. Step 1. Step 1, you have to ask. Okay, one is defined. Okay, so first thing you need to check is f0 defined based on the function given above. It is this, and the whole world knows that sine 0 is and cos 0 is, so therefore 1 is true. Number 2, you have to check for the limit. And in this case, because the function is defined differently over the two different sides of 0, you therefore have to find the limit in two parts. You find the limit on the left. Now, when you find the left limit, we prefer that you write down. We prefer you write down which function are you using, so that we know that you know. In this case, 0 minus must be the sine x plus the cosine x. Huh?
Are you allowed to present your working with like a 1, 2, 3?
Yeah.
Or must you write the condition stuff?
No, okay, 1, 2, 3, can. If you like 2, you can call this 2a 2a. So this is going to be 1. Then 2b, limit x goes towards 0 plus. Then this is going to be x plus 1. And this gives you 1. So therefore, this is equal to 1, since by 2a and 2b. 2b. Then now you can draw your conclusion in step 3. This O2 is true. Step 3, right? You will see that is indeed equals to f of 1 equals, I was kidding.
Oh, she was just testing you.
Yeah, testing you. So it said therefore by 1, 2, and 3, function f is continuous at x equals to 0.
If it fails 1 or 2, then you have to choose.
Yeah, no. You all sleep well in the morning?
Yes.
You have a king coin bed?
Huh?
Is it king coin mattress?
Yes.
King coin mattress.
Yes, good God, I don't even know what kind of mattress it is.
You can bring your own one. You can just bring your own mattress. Very heavy.
You know we have king size bed like mattress. Bring a mattress out.
Really?
Yeah.
Show of hands. Who have ever slept on a water bed? Instead of filling in with cotton, it's filled with water.
Is it nice?
Okay, long ago, I was driving all over UK with another friend, and then it was snowing quite heavily, you know. And come to a point we just cannot go on anymore. We stopped over at the pub. Upstairs, they have rooms to rent to people, no? So that was when I experienced water bed for first time. Very uncomfy, you know. Because they only give us one bed. We are both guys, okay? You have no choice to share the one bed, you know.
So you sink in it.
When one guy move, right? Just Allah! Epic, you know, epic, really epic.
When your friend is sleeping, right? Can you jump on the bed, then he'll fly out.
Maybe, you know. So we had to say, don't move, no, don't move. Just stay put, you know. Okay. Let's try this one. It says it is continuous at x equals to 1. The moment it says the function is continuous at x is 1, what can you say? Immediately the limit as x goes towards 1 of fx this kind of question tests you on your concept of continuity. So the very first line you want to do is to make use of the condition. In fact, you realize that the condition I'm using is the third one, which encompasses the first two actually. No? Right? It's all in one. So based on this, you now want to calculate the limit at x is 1, and of course the function value at x equals to 1. So now we press on to find the limit at x equals to 1, and this is root of x plus 3 x minus 1 equals to f of 1 is equals to c. And you already know by now that for this kind of question, to resolve the limit class, what do we do? We multiply by the, yeah, right. Okay, now we can do this now. Avoid L'Hopital in chapter 1, you know, because we are trying to enforce this so that you want to make use of the other known methods. See? L'Hopital is very useful. That I got to agree with you. Right. Then after all the tidying up, check, you know, whether or not we all are agreeable to getting this.
Yes, let's resume.
Gyro is back now. Gyro, where's Gyro? Coming in here. Okay, Gyro is coming in. Okay. Now that we learned how to actually prove continuity at a point, we now want to look at so-called result 1.9, wherein it lists down for you. It lists down for you the common functions and the fact that they are continuous. So when you deal with this kind of functions, right, you can just assume they are continuous. You don't have to go and prove, you know. Like for example, x squared plus 2 is continuous everywhere. It's a known fact, you know, given in result 1.9, bracketed part 1, and so on and so forth. Okay, right. Okay. Now let's move on to this. These are very wordy definition, you know. Continuity on an open interval. For continuity on open interval, it means it is continuous at every point on the interval. Continuity on an open interval is not too bad, it's quite easy to just comprehend because it means it is continuous at every point on the interval. The problem comes when we talk about another thing later. So let's look at this one first. Okay, for example, right? These are the open interval, right? These are examples of functions which are continuous on the open interval. Okay, now, if you have this one is a bit tricky, you know. This one is a bit tricky. Why is it tricky? Because for a closed interval, right, the limit at the endpoints become very vague, you know. Because at the endpoint, you only can talk about the one-sided limit. Can you see? So therefore, for continuity on a closed interval, the only exception you need to make is at the endpoints on the left side and the right side, that the condition is a bit weakened to only one-sided limit equals to the function value. You know, that's something you want to know. You know what I mean?
Yes.
And then with these two statements, right, you can just extrapolate to discuss about continuity on the closed open interval. One side closed, one side open, and open and closed interval. Let me say, how about continuity on such an interval? The same thing goes on, just like you got to take care of the endpoints, right? So be very careful about continuity on intervals where you have closure on one side. Okay. Then there are some examples for you. Okay. Continuity on a closed interval. Someone asked before, no? Say, do you realize this? Someone asked, no, hey, Mr. Lim, why is this? And the way to see that this is closed is because the opposite of this. What is the complement of this interval? What's the complement of this interval? And because the complement is actually an open interval, therefore this other one is called a closed interval. This is how it's judged. Yeah. So whenever you have involved infinity, right, things may be a little bit different, you know. Just like do you know like that plus like this is not too bad, but like this minus like this, right? You can't say it's 0. If you say this is 0, right, then after all this is not really that big. Okay, anyway, let's do example 23. From the graph, it's obvious, you know. Is f continuous from the left at b? So imagine an interval that's something like this. Doesn't matter what you have to cite. Okay, so we're talking about this now. Do you consider it being continuous from the left at b? And the answer is yes. How about continuity from the right at b? So imagine an interval that is like this, no? And this is no. Okay, and it refers to this portion here. Okay, and this is yes. Continuous on a closed node. See, here, this point A is inclusive, you know. Yep. Right. Then there are okay. Okay. Many times, if a function is continuous, you want to ask, no, function that resulted from a continuous function, do you think it will always be continuous? For example, if you have a function that is continuous, you are interested to know if this is true. And you know that the function f and its inverse, right? They are just a mirror image. If you mirror image yourself in a mirror, do you expect to see a different person? No, right? So likewise, in the case of inverse function, the answer is if a function is continuous, so is the inverse. So there's a word example here. The function and its inverse. This function is known to be continuous. Why is it so? Because earlier on I told you, polynomial is well known to be continuous. And then in this case, right? In this case, the inverse of this function, which is this one. These two are inverses of each other. No? Okay. So G is actually F inverse. No? So because of this, since the function fx is continuous, the inverse will also be continuous. If a function is continuous, a resounding function such as the reciprocal, class, do you think that if this function is continuous, do you think that automatically this one will be continuous? The reciprocal. You think so? Do you think so? Yeah. If a function is continuous, do you think the reciprocal will be continuous for sure? No, it's not. Okay. There are a lot of examples you can come up with. Do not mix up inverse with what do you call this? Do you know why that people have a confusion over these two notation? Because in numbers, right? In the case of numbers, their inverse and reciprocal are identical, you see. So for the reason people are confused, you know. But NUS high student will not. I'll wait for you to come up with one. If you come up with a good notation, don't tell people about it first, no. Remember that. Just come to me first. Okay. Example 27. Show that cos inverse x is continuous. So to do this, right, you want to start out by this one first, no? sorry. So look at fx. This function, right, is okay. Maybe I should write this thing down. Hence, its inverse. The inverse in this case is gx now. Okay. Okay. I want to put this thing. Samalah. Okay. Is also continuous on the domain of G. And what's the domain of G? It is -1 to 1. To find the domain of an inverse, in case you have forgotten, the domain of inverse is just the range of the function. And of course, the precursor to have inverse is what? The function is, what are the condition needed for a function to have inverse? Bijective. And what does bijective mean? Brilliant! Aditi, you're right. A good learner. Onto. Yeah. Onto. Okay, since you asked surjective means onto. Meaning to say that, okay, what's onto again? Meaning to say that there's a term called codomain, you know. Have you heard of it? Yeah. The codomain is the same as the range. The A-level students don't learn about onto-ness at all. No? Yeah, they don't learn. They just assume to be onto, no, for the A-levels. Yeah, they don't have this term subjective in the syllabus anymore. A-levels. But we are special. We are exceptional. And moving on, given two functions which are continuous, you produce a new function. The sum, the subtraction, okay. The last one, there's a catch. The last one, there's a catch, you know. This is a needed condition. You. Must you prove that this function, this one must prove first, is it? You're saying? Okay, maybe for this case, our focus is about continuity, nothing, no need. Yeah.
Then must you prove that the range is
one
negative number?
I think for this question we probably don't, because our focal point is this. So we assume that you have very good foundation in functions, and you therefore are able to cite this because you know that the domain of G, which is the domain of F inverse, is from the range of F. We assume that you know. Yeah. Where did you learn this topic, functions, in your school here? Year 3. The schools in Singapore don't learn it in secondary school anymore. They only learn in JCs. But if you're from IP schools or like St. Joseph, RI, I think they learn it. Yeah. I know ACS also you do it. But the vast majority, they learn it in JC. Have you learned P and C? The secondary school don't learn it anymore. They only learn it in JC also. Yeah. Permutation and combination. Yeah. You learn it in year 3, right? Year 2, okay. Okay, class, then to write down the proof, there's a remark given to you here. If you like to prove those statements that we made earlier are true, you can actually just, read this remark here. Okay. This is a very big thing, This one, you got to look at it very, very carefully, For example, okay, for example, like that. Okay. So in this case, right, if you see your fx, right, as sine x, and your gx as, okay. So supposedly it is like that. So then your f of gx is exactly this thingy, What this result aims to tell you is this, that if you ever need to find the limit of such a function, such function they are called, very good. Aditi learned her stuff well. Having good memory is also a talent, When I was a policeman, NS. I had a senior in the police, as in the person who bring me around, my mentor, so to speak, in the police force. He has very good memory. He remember a lot of car plate numbers. Very good, You know why? No. You know why he can remember car plate number is good? Because sometimes you go on petrol, right? We are given a long list of stolen vehicles. So he just put a number. He said, I think it's in the list. Correct. We do. I tell a very sad story, My own colleagues in the police force, he stole vehicles and he drove into Malaysia. And how did he get by, Because in my days, policemen with warrant card can go through a customer, Singapore customer, without being checked, because they just show a warrant card. In my days. Now cannot again. Too many of this nonsense. Sad. He was caught eventually. Not military police, the blue uniform police, real police. In my own police experience, sadly, another colleague of mine killed himself inside a police station. Shot himself dead. Committed suicide. Very sad. Yeah, I didn't have a chance to ask him why. Yeah, he was, I guess he was having a lot of stress. Policemen are very stressed, That's why in the Home Affairs Minister, when he talked about investigators having lapses because they're overstressed, I can understand, I was working like 8 a.m. starting this morning till 8 a.m. the next day as a police investigator. And you think that after 8 a.m. you go home. No, at 8 a.m. the next day, if I have other cases like dead body in the mortuary, I had to drive down to the mortuary at SGH and stand by there at 9 a.m. to receive the next of kin and to bring them in to say, that's my relative. In the press, why 9 a.m. Because at 9 a.m. the state coroner will drive down to the mortuary. He will be there.
Why do you need to be there?
policemen do all kind of saikang, you know. Then if you're lucky, after that meeting with the coroner, nothing happens. You got no more accused person in the police custody. Then you go home and sleep. But if you reach home at 10 a.m. and then they call your accused has been arrested already, then you have to come back to police station. So when Home Affairs talk about this stress of the police investigator, I can appreciate it because very stressful, no? Very stressful. Yeah, so I'm lucky, it's just NS. I'm now very happy to be a teacher. I have long holidays, no? I enjoy the holidays. I traveled a couple of times to Malaysia. I drove and I used math to beat the traffic jam. Okay, in any case, class, this is a very important result that you don't forget, you know. Basically, it means, class, you can bring in the limits. You know what I mean? Bring the limits into the function is not always true, but we are telling you that this will be true. There are certain things that we think is obvious, but it's not, you know. This thing actually requires a bit of a justification, you know.
So the only condition for this is the inside function must be continuous.
No, the outside function.
Okay.
Function f.
Oh, F is outside.
And the limit inside must exist. The limit inside must exist and the function outside must be continuous.
So the inside does have to be continuous.
Yeah.